بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. طيب, for today's lecture inshallah, we are going to talk about these basically subjects. أول حاجة, first thing, I'm going to introduce you to Terasic's system builder tool, okay, where to find it and download it and how to use it. Simple as that, okay? And also I'm going to repeat time quest timing analysis, okay, in which you correct the timing errors that you get after synthesis. I'm also going to introduce the platform designer. I'm not going to, of course, talk about it completely. The platform designer is a big subject, okay, but I'm going just to use it to use what we call PLLs in order to create the frequency that your circuit can operate at. And all of this is going to be discussed in the context of a square root calculator, that once again, another square root calculator, which is called Heron's square root calculator. And this calculator now, it will actually calculate the exact square root, not just the what we call integer part, but also the fractional part. And for this reason, I'm hoping that you guys have already studied fixed point systems, okay, fixed point systems, because number systems, because I'm going to make use of these systems. Okay, so for this application here, I'm going to go over the pseudocode and then ASM chart and then Verilog code. Then we will verify that the Verilog code works, and then we go over the implementation, and hopefully I'm going to show you the circuit up and running in the DE1 SOC or SOC board, okay, that we have, right, that you can actually borrow for your project, okay. Let's start with the pseudocode. I'm going to start from here now, okay, and then cover these subjects as we bump into them, okay, as we need them, all right. So let's start with the pseudocode of the Heron's square root calculator or algorithm. Sometimes this is called also the Babylonian square root calculator, okay. For a square root calculator, you need to have a data input, and also for any circuit that has interaction or user interaction, you have to have an input that synchronizes the user input. Okay, so at the beginning, we are going to wait for this is the first action in the circuit. Wait for a positive edge on go. Once you receive that, you latch the whatever in data in into a register called S, okay? And this is the square that we want to find its square root, the squared number that we want to find its square root. I'm going to have an initial guess of my square root to be basically S divided by 2. Okay, if the number is 4, I'm lucky. That's the square root actually, because 4 over 2 is the square root of 4, right? But it's only the case that is true in the case of 4, but other cases it's not true. So we can use this as actually a starting point. Next, I'm going to invoke only 5 iterations of this update, okay, of the Heron's square root calculator. It turns out that 5 iterations are actually enough to get an accurate square root calculation. Okay. And just to show you the Wikipedia page for the Heron's method, this is the, by the way, Shabab, do you see my screen? Am I recording the screen? Am I recording the screen? Yeah. Okay, good.
Yeah, it's clear.
All right. So this is the Heron's method. It's simple, actually. You start with a guess, okay? A guess of the square root that is greater than 0. Of course, the square root has to be greater than 0. And then the next guess, which is x sub n plus 1, is basically the average of the previous guess, which is x at n, and s divided by xn. Okay? So if you take the average of these two quantities each time, okay, and then you update xn, okay, each time, you'll wind up at infinity, you'll wind up with the square root of n, okay, of s, I'm sorry. So the limit of x sub n as n approaches infinity is the square root of s. All right? Right. So this is exactly what I was just doing. So there is no need actually to keep track of the previous x's. So you can actually replace this x sub n plus 1 and x sub n with x, just x. Okay? This is x, this on the right hand side, it is the current value, and on the left hand side, it will be the next value, right? So if I get back to my pseudocode, now this is s divided by x, and I'm calculating it as a combinational signal here. Okay, it is basically s shifted to the left by scale. And this is the scale. The scale here is the number of fractional bits. For those who have watched the fixed point arithmetic, they know what I mean here. So basically what we're doing here essentially is a fixed point division of s divided by x, okay? And this shifting to the left by scale is for the correction of the scale, okay? If you are in doubt or somewhat lost here, please go back to the lecture on, which is 21 minutes, I believe, on fixed point arithmetic and watch it, okay? This should make perfect sense to you. And then the new x, is going to be assigned to all the average actually of all x plus s by x. S by x is this one, okay? And then, of course, I said the average, but of course, the average is taken by basically shifting this quantity to the right by 1 bit, which is effectively speaking, basically is the same as dividing by 2. And then I increment the iterations by 1. Okay, and I check here. If iterations does not equal 0, go to 3. Do that again. Otherwise, my ready equal 1. This is a combinational assignment. And my d out is equal to 1. Now here, this is also a combinational assignment. This is a sequential assignment. So make sure that you differentiate between sequential assignments and combinational assignments. Okay, it's very important to distinguish between them. Clear, ya shabab? Now our objective is to go from here, to awesome chart. Yeah, it's easy, right? It's super easy. But before that, I'm going to assume that I have a data path component, okay, called positive edge PGO, okay? It just produces PEGO, okay, which is 1 when we detect a positive edge on Go. That's much easier, okay, to have, because If we don't have it, basically the algorithm will get a little bit. I mean, the ASM chart will get somewhat longer than needed. Okay, longer than needed. So here, instead of saying wait for a positive edge go, you can actually replace it with if not P go to 1. Otherwise, otherwise you stay, you continue to 2 here. I forgot to say go to 4, yeah, because there is nothing. This is يعني in pseudocode يا شباب, in pseudocode, unlike Verilog, of course, it is assumed that you always go to the next step. Okay, if there is no go to, there is a go to, and you go to the line number. Otherwise, you go to the next step in the pseudocode. However, in Verilog, unless you change the state will remain the same. Okay, the state will remain the same if you don't change it. Any question, Shabab? Any question?
دكتور انه ما راح يتغير الستيت في الفيرولوج اذا ما حددته.
هنا
لا انت قلت في الفيرولوج انه
قطع صوتك يا cutting off.
كنت اقول يا دكتور صوتي واضح.
Your voice is muffling. يعني it's like يا شباب, can you hear him right? I think the problem from your end or from my end. I'm trying just to find out if the problem is from my end or your end. Anyone can comment on that? Can you hear تميم؟
في تشويش شويه يا دكتور صوتي
يقطع صح؟ اي
بس اللي بكتبه.
Can you write your question on chat, please, so that we have a look and tell you. All right. So with this, I think we can go to PowerPoint while Tamim is preparing his question on chat. All right, and then start. Let me put the pseudocode on this side here. We can actually. Okay, so we have insert. Nope. Not this one. Actually. Oh, yeah. And then oh. All right, so this one here is the reset state. And to indicate that, I can say, well, here this is, I don't know why it's, where is the text? Insert text box. No, not comment. I'm trying, ya shabab. Anyone can tell me where is the insert? Oh, it's in another menu. Okay, so this is what? Reset, huh? Reset. And inside of this, there is nothing actually. The first, I need the diamond now. Oh man, this is taking so long. Okay, you know what? I'm going to pause recording until we finish drawing the ASM chart, and then you remind me, please, to start recording again, okay? so that the video doesn't become longer than needed. All right, so this is the final awesome chart. We have the initial state here, S0, and then we check for a positive edge on go. There is a circuit behind the scenes here, okay, that takes go and then produces this signal, which is positive edge on go. All right, we'll write that down on the module, okay. And then if it is 0, then we stay here. Otherwise, if it is 1, we detected positive edge on go. We will initialize S, X, and ITE, and then move to the new state. In this state, we continuously update X. Let me just put a new line here so that things come clear. X with the average of the current value of X and S by X. And then we decrement. The beginning we said increment, by the way, the algorithm, but it's been corrected to decrement the iterations. And then we move to this decision box. If ITE does not equal 0, we get back to S0. Otherwise, what do? We can actually have to add another state for the end, yeah? For the end. Let's...
Doctor?
Yep.
In state 1, S by X, I think it should be a sequential statement, non-blocking assignment.
This one?
S by X shouldn't be a non-blocking assignment.
No, you don't have. No, it doesn't have to be. No. But I'm just calculating it here because it will look ugly if I just take this and replace S by X with this. Okay. So I have broke it down into 2 statements. Okay. And this X here is the old value of X. It's not the new. It's not the one that is going to be updated. Okay.
Yeah, okay. Yes.
Now this is what? This is when we have 1 here, and when we have a 0 on the other hand. 0. We go here, right? Insert. And here we do 2 things. Ready equal 1 and data out equal X, right? And in this state, we just keep going back the same state, yeah? Same state. Is that clear, Shabab? Okay, so we winded up with 3 states instead, okay? 3 states. Hold on a second, let me finish this part and then finalize the S2, okay? That's S2. Abdullah, I believe, yeah? Abdullah,
Yes.
ask.
Doctor, when do we know that it's safe to use blocking assignment inside the state?
Blocking assignment. This is just a specification. I just made it up. I'm just using these signals. Whenever you enter S2, ready should be 1 and the out should equal to X. That's it. Okay. This is made up. All right.
But isn't it better to make it?
Because I made it this way in the pseudocode itself.
Okay, in general.
Yeah, in general, it depends on your requirements. Okay. So you can assume this or that. All right. Yani, what is the difference? What is the difference?
I remember, like once you mentioned that we should never try to use blocking assignment inside an always block.
No, I didn't say that. I never said that. Maybe you misunderstood. You can use blocking assignment. The
Yeah,
better
we
name,
can.
yeah, the better
We
name,
can, but you
better.
said it's dangerous. It's very dangerous to use it.
Yeah, it is dangerous. It is dangerous. What I'm saying here is that don't mix assignment inside an always block. Inside the same always block. This is what I said. Inside the same. This is in Verilog, not in Asm chart. Okay, in Verilog,
Oh, okay,
same
clearly.
in the same always block. Do not mix assignments. It will be wrong. Okay, because you might get it right, but it is very difficult to get it right. Okay. طيب. So let's
Doctor,
yeah.
why are we not replacing state 2 with conditional box to reduce the number of states? I think it will work also.
No need for conditional box, and I don't want to go back. I don't want because if you go back, you'll keep updating. See?
لا لا أقصد ال state 2.
No. Then you have where do you go after that?
So maybe the conditional box itself.
To the decision box, right?
Yeah, or to the decision box.
This is a combinational loop. It's not allowed.
Oh, okay.
So there is no getting away with another state. Yeah.
Yeah, okay.
All right. So great. Let's put this aside and then try to write the module. Okay. And say square root. Right? It takes clock. It takes reset. And it takes a data input and what? Go and data out. Ready. That's it, right? So input, block, comma, reset, comma, go. Yeah. Input. Let's say that my data n is 8-bit. 1 to 0. Data n. And my output ready. Okay. And output 7 to 0 data out. I have to have a register called S, right? Let's use a small s just for the sake of and the register called X, yeah? Both of which are 8-bit, okay? In fact, I think 8-bit is too small. So let's use because we want fractional, right? So let's use 31 to 0. 31 to 0. And let's define as a parameter here. Let's define local parameter. Local param. Define our scale, yeah? The scale to be how many fractional bits do we have out of 32? Let's use, for example, I don't know, maybe 12. Yeah, 12-bit for the fraction. Yeah, I think that's enough. What else? We need S by X, right? But this is going to be S. I'm going to write that down in a moment by X. But for this, I need more bits than just 32, because what I'm going to do is to, if you see here, I'm going to shift S to the right, to the left, I'm sorry, to the left by scale, by 12 bit. So I'm going to assume at least 12 bit more, okay, for S by X. And then I'm going to correct that by taking the lowest 32 bit. All right. Anything else? Did I miss something? Maybe the ITE, yeah? Register. That's just a 7-8 bit ITE. All right. By the way, Shabab, if I say equals 0, what does it mean?
7 bits صار 0.
Come again?
Is it that's all the 7 bits are 0?
Okay.
Initializing.
Yeah. Who said initializing? That's Weva?
Yes.
So initializing what? What do you mean? Can you elaborate?
Initializing the 8 bits to zeros.
طيب. Now, when I synthesize this on our board, will it do that for me just by doing this? Will it initialize LTE to 0 just by doing this?
I don't know, but it's very abstract because we should do a loop and maybe, I don't know actually.
Answer to that is no. It won't, because this one here is equivalent to saying, well, there is an initial block where I say ITE equals 0. That's it. Without begin and end, because it's a single statement. You can add a begin and end here, but it doesn't matter. And the shortcut for doing this is this. Okay? All right? Oh, this is only for simulation. For synthesis, it won't do that. Okay, it won't initialize this register to any value. Okay, in order to initialize it, you need to add logic for that. You need to add logic at reset. And what else? We have local param again. The states is 0 equals 0, S1 equal 1, and S2 equal 2. Right? But before that, I want to generate the PE go signal, yeah? So I have an always block, always at positive edge on go, not go, clock, sorry. What do I do? If, actually, there you go, is go, actually, yeah, the current value is 1 and the previous value is 0, yeah? The previous value is 0. And I have, for example, actually, I need the begin and end here. Okay, so let me just take that back. So register prev and wire ego is equal to go and not prev. And here we just say prev gets what? Go. All right. This is Prev is always the previous value of go. All right. So if the previous value of go was a 0 and the current value is a 1, then this is a positive edge on go. All right. Got it يا شباب؟ طيب, now we can define our okay param. Did I write that? Okay. I did that. And then I have to define my state register, which is, in this case, how many bits? 2 bits, right? 2 bits. Next, I start my always block at the main always block, positive edge on clock, begin, and end. There is an end module. By the way, I should have created a new file for this, but I don't know why I didn't. If what?
Reset.
Yeah, RST. Yeah. RST. Actually, I'm going to make it negative edge, negative, what is it called? Active low. Okay, active low. Because I'm going to hook it up to a push button rather than a switch. Then my state is going to be S0. Else, now I have a case on state. Right? If you are in S0, what do? It's just, let me just, yeah, if you are in S0, you just check what? Positive edge on go. State is going to be, actually you have an F statement here, better. F P go, or positive edge on go, then begin, S gets DM, and X gets, okay, so here, this depends, we cannot say S because S hasn't been latched yet. So we can actually use DN again because DN is the same port and we are sampling it for S as well as X at the same time. So it is going to take the same value. So this is just the data N divided by 2. And then ITE gets 5, okay? Also, I need to go to state what? S1, yeah? And S1, what do I do in S1? The first thing is, not the first thing actually, but begin and end, yeah? S by X, okay? Actually, this is a combinational assignment, so I don't do it here. I have to do it inside of an assigned statement, right? So I have my module here, and inside my module, somewhere, I can insert it anywhere I like. Let's say after the definition here, I can say, well, this equals, first of all, state. If a state equals this one, then what? Then I will actually give it S shifted to the left by scale. Okay, divided by X. All right, divided by X. Otherwise, it is 0, but it is what kind of 0? It is 43, yeah, or 44, is it? Yeah, 44 bit 0. Okay, is this clear, Shabab?
Doctor, can you repeat this last thing you did?
This one, you mean?
No, the whole line. This whole line. Why are
Yeah,
we like?
S by X is a combinational assignment. I'm using an assigned statement here. I'm checking if it is, if the state is in S1, then I'm going to actually assign it to S, shifted to the left by scale divided by X, as shown in here. Okay?
Yeah, yes, exactly.
Otherwise, if this is not true, I'm going to assume that it is 0. Okay, you can put 0, by the way, and have some warnings in your design. تمام.
وش معناته دكتور الاتش 0 او الاتش بالاصح؟
H is hexadecimal. تمام.
طيب واضح.
You can say decimal, you can say binary, 0 كله. It works for everything. Okay. So this is for S by X, and the X now, I can calculate it actually. It is basically X plus S by X, but shifted to the right by 1. Okay, this is just the average of X plus S by X. Okay. And also, I'm going to decrement iterations by 1. Yeah. And check now if, in fact, here, by the way, Shabab, I'm checking if ITE does not equal 0. Right? Yeah, let's just implement the exact same version of the algorithm. Okay, if ITE does not equal, actually, if it equals 0, which is the complement of that, I'm going to go to S2, right? State gets S2. And in S2, I'm going to just relax, do nothing whatsoever. Okay, because both of my assignments are combination. Yeah. And S2, I'm going to do nothing here. All right. On the default case, I'm going to go to the initial state. Right. We still have to implement ready and the out. Yeah. So we can say here, assign ready to be equal to if state equals S2 and ready is 1. And assign my D out to be if state equals S2, then D out is going to be X. Otherwise, it is 0, let's say. But D out is what? 32 H0. Okay, Shabab? By the way, Tamim, this should look familiar to you, okay? So please go back and review basic Verilog, okay? This is almost all of it. Let's just create a new file and paste that here, and then save as. Let's go to documents and then projects. and then square root. And let's save it here as square root dot v. Notice the double quotes because this is just notepad. Yeah. Now you get the color coding there. Okay. So let me just stop the video. Okay.